3 hours and 12 minutes. That is all the warning Rotterdam gets before a North Sea storm surge tops the quays and swallows a city built 7 meters below the ocean's surface. Not a hypothetical, a calculated deadline run by computers, confirmed by tide gauges, ticking in real time. Every Dutch flood barrier built before 1997 fails under exactly these conditions. Too slow, too rigid, or simply too small for the Nieuwe Waterweg, the open throat connecting Rotterdam's port to the open sea. What the Netherlands finally engineered to close that gap came down to one gate, one decision, and a hydraulic gamble 4 centuries in the making. What follows is a reconstruction of every decision point that made that gate the only possible answer. Rotterdam is not just a city, it is the economic spine of an entire continent. The largest port in Europe moves roughly 470 million tons of cargo every year. Pharmaceutical supply chains, automotive parts, crude oil, grain, all of it flows through a delta that sits below sea level. Remove Rotterdam for a single day, and supply chains fracture across 12 countries. Remove it permanently, and the Netherlands loses roughly 65% of its GDP. That is not a recession. That is national dissolution. Behind the port, 4 million people live on land, the sea already claimed once before. The flood of 1953 killed nearly 2,000 Dutch citizens in a single night. Engineers measured the aftermath in bodies and in silence. The pressure to seal the Nieuwe Waterweg was immense from the moment the floodwaters receded. And yet the final gate did not arrive for 44 more years. The question is not why they built it. The question is why it took that long. That interval contained 5 rejected designs and 1 engineering argument that went on for decades. Each failed proposal addressed the inlet's width and the port's need for open access. Each collapsed under later scrutiny of storm strength or shipping lanes. Understanding why requires going back to the night everything broke. January 31st, 1953 began like any winter storm. By morning, it had become the worst natural disaster in modern Dutch history. A spring tide was already pushing water landward. Then a North Sea gale arrived from the northwest, stacking that surge higher. The combination was not predicted in time. Warnings did not reach coastal villages. People slept. At 5:30 in the morning, the first dike gave way. Then another. Then dozens more. By dawn, 89 dikes had breached simultaneously across the southwestern delta. Entire polders, land sitting below sea level, drained and settled over generations, simply disappeared beneath the water. Farmhouses stood with rooftops showing. Livestock drowned in their stalls. Families climbed into attics and waited. When the water finally receded, 1,836 people were dead. 72,000 were homeless. 450,000 hectares of agricultural land were submerged in salt water. The Dutch Parliament met within days. The question before it was not whether to act. The question was what kind of action a small, flat nation could sustain for the next century. The answer they chose reshaped the entire coastline. The Delta Committee published its report in 1958. Its logic was simple, almost brutal. Close the inlets, all of them. Build dams across every southwestern estuary where the North Sea had found its way inland, and turn a fractured coastline into a controlled one. Over the next 4 decades, that is precisely what the Netherlands did. 13 primary structures. Dunes reinforced, sluices rebuilt, tidal channels blocked. The sea was not defeated. That framing is too dramatic, but it was given fewer doors to walk through. Each closure followed a pattern. Engineers studied the inlet, designed the barrier, built it, and moved on. The water on one side stayed saline. The water on the other side gradually freshened. Ecosystems adjusted, sometimes badly, sometimes better than expected. The program treated nature as a variable to be managed. Every inlet yielded to that logic, until the program ran into Rotterdam. The Nieuwe Waterweg is the shipping channel linking Europe's largest port to the open sea. Close it, and Rotterdam stops. Close it, and the German hinterland loses its primary Atlantic gateway. The Delta Committee had mandated closures. The port economy had other ideas, so the final inlet stayed open. For decades, the most dangerous gap in the Dutch flood defense remained the one nobody was politically willing to seal. Before the solution to that gap becomes clear, it helps to understand the cost of the compromise that came just before it. The Eastern Scheldt Barrier was built to protect one of the southwestern estuaries while preserving its tidal ecology, and it became the Delta Works' clearest demonstration of what compromise actually costs. 65 concrete piers were sunk into the estuary bed. 62 sliding steel gates were fitted between them. 9 years of continuous work produced a structure that could shut out the North Sea during extreme surges, yet allow normal tidal exchange on every other day. The estuary's salt marshes and shellfish beds remained intact. The price of that preservation reached 10 times the sum first budgeted for a conventional fixed dam across the same inlet. The barrier proved that partial closure could protect both land and living systems. But the Eastern Scheldt Barrier left the original problem of the Nieuwe Waterweg untouched. If the Eastern Scheldt had already solved the compromise problem, why could the same design not be applied to the shipping channel that still linked Rotterdam to the sea? The answer starts with a single measurement: scale. The Nieuwe Waterweg is not simply another estuary. It is 360 meters wide and 17 meters deep, a corridor carved by the Rhine itself, scoured by centuries of tidal current, into something closer to an open canyon than a river mouth. Every year, 30,000 ocean-going vessels pass through that corridor. Container ships, bulk carriers, and tankers drawing nearly 15 meters of water all pass through daily. Any structure interrupting that transit, even briefly, would not inconvenience a city. It would fracture a supply chain that feeds the entire northern half of Europe. A conventional flapgate, the kind proven in the Thames Barrier, requires a sill across the riverbed. A sill here would reduce navigable depth. A caisson gate requires time to position and seal. Time on a waterway processing 80 vessels a day is exactly what engineers did not have. A fixed dam was never considered. So Dutch authorities assembled 5 independent design teams and asked each one to find a geometry that could work. Each team arrived at a different answer, and each answer, when subjected to the same practical test, failed in the same way. The first team proposed a pneumatic rubber dam, essentially an inflatable tube, anchored to the riverbed, that would rise when air was pumped into it and block the incoming surge. The concept had worked on smaller waterways, but the Nieuwe Waterweg carries tidal forces powerful enough to deform and eventually rupture a rubber membrane at the scale required. Material fatigue would arrive long before the structure paid for itself. The second team looked downward. A submerged tunnel gate, resting on the bottom in normal conditions, could be raised hydraulically when a storm threatened. Sedimentation killed it. The Rhine deposits roughly 12 million tons of sediment per year into this estuary. A gate mechanism buried in that riverbed would be entombed within a decade. The third team borrowed from Venice, a flap barrier hinged at the seabed, lying flat when dormant, rotating upright under water pressure. The tidal range here is nearly 2 meters, creating differential pressures that would force the flaps to cycle constantly, accelerating mechanical wear past any acceptable maintenance budget. The fourth proposal was a retractable bridge gate hybrid, a structure that could serve as a road crossing and then withdraw into abutments during a flood event. The numbers on steel tonnage and foundation depth ended the conversation before it began. The fifth team specified a vertical lift gate. The required lifting height, combined with the span, produced a structure whose own weight exceeded the capacity of any crane system then in existence. 5 teams. 5 distinct failure modes. And yet, buried inside that pattern of failure is a single variable that every proposal had in common. One that the winning design would approach from an entirely different direction. That shared variable was bending stress. Every gate, in every configuration, attempted to hold back water by resisting the load through its own structural rigidity. Given sufficient pressure and surface area, water will always find the weakest point in a rigid system and break it there. Each of the 5 teams had essentially asked the same question: how strong does this structure need to be? And arrived at an answer the available materials and budgets could not satisfy. The team led by designer Wim Quist asked a different question entirely. Instead of building something strong enough to resist the force, they asked, what geometry transforms that force into something a structure already knows how to carry? The answer was rotation. That principle took physical form as 2 enormous hollow arms, one anchored to each bank of the Nieuwe Waterweg, would swing outward from their resting positions on dry land and meet at the center of the channel. Each arm connects to its concrete foundation, not through a fixed joint, but through a hollow sphere, a ball joint more than 10 meters in diameter. When water pressure bears against a closed gate, the load travels along the arm toward that sphere, and the sphere transfers it directly into the concrete as pure compression. There is no bending moment. The material is doing exactly what steel and concrete do best. This is why the arc geometry was not merely elegant. It was the only shape that could redirect hydraulic force rather than absorb it. The gate folds away on land, deploys in under an hour, and in principle carries millions of tons of water pressure without a single bolt working in bending. In principle, though what those ball joints would actually experience under 10 million tons of load was a question the engineers could not yet answer when the design was approved. Each arm stretches 237 meters. That is longer than 2 Boeing 747s placed nose to tail, and the entire length is fabricated from curved steel plate. Not straight sections welded into an approximation of a curve, but genuinely curved members formed to follow an arc. The curvature is not decorative. It ensures that forces travel along the arm's axis rather than across it, keeping the steel in compression where it is strong and out of bending where it is vulnerable. At the end of each arm hangs a gate sector. These sectors look solid. They are not. Each one is a hollow steel shell, sealed tight, and that hollowness is the mechanism. When the gates are deployed across the waterway, they float. Then, seawater is pumped deliberately into the interior chambers. The sectors grow heavy, sink to the riverbed, and press against a concrete sill. The seal is made by dead weight, not by clamping or latching mechanisms. When the storm has passed, the water is pumped back out. The sectors become buoyant again, rise, and the arms retract. The gates return to their resting position inside 2 enormous dry docks carved into the riverbank. The docks are not storage. They are structural. When the gates sit inside them, the dock walls and the gate become a single unit, and the whole assembly reads as ordinary riverbank to a passing ship. This structure was named the Maeslantkering. It opened in 1997, and it brought with it a question that the engineers had debated since the design was first approved. Who decides to close it? The answer is no one. A computer issues the command autonomously, and human override is locked out entirely. That decision is worth pausing on, because it is not a default. It was a choice, made deliberately, after studying what happens when humans are inserted into a time-critical flood closure sequence. The record showed that operators under pressure hesitate. They seek confirmation. They wait for one more data point. On the Thames barrier, human judgment is part of the loop, and that works. The Thames narrows predictably, and tidal forecasting, there carries less variance. On the Nieuwe Waterweg, the forecast window is shorter, the surge dynamics are more complex, and the cost of a missed closure is measured in human lives, spread across a city of 4 million people. Removing the human from the final decision was not a concession to automation. It was the engineering response to a documented failure mode. The system that runs the closure sequence is called BOS, Beslissing Ondersteuningssysteem, or Decision Support System. It runs continuous hydrodynamic models, ingesting real-time data on wind, pressure, and tide across the North Sea. Those models generate a probability distribution for water levels at the gate over the next 48 hours. When the forecast shows a surge crest exceeding 3 meters above NAP, Dutch Ordnance Datum, the national sea level reference, BOS issues the closure command on its own authority. The 3-meter threshold was calibrated for an average activation rate of once per decade, balancing flood risk against the economic cost of blocking the port. The models remain probabilistic, incorporating uncertainty bands that widen with forecast range. BOS therefore waits until the lower edge of the confidence interval itself crosses the threshold before committing, reducing the chance of an unnecessary closure driven by an outlier simulation. Once BOS commits, the sequence runs to completion, 60 minutes from command to sealed sea. The first act is counterintuitive. Water floods into the dry docks, not out of them. The hollow gate sectors rest on the dock floor and must become buoyant before they can move. Pumping seawater beneath them lifts each structure free of its cradle and sets it floating in place. Then the motors engage. Steel cables and rack and pinion drives begin rotating the truss arms along their arc. The motion is slow enough to observe with the naked eye, yet each arm sweeps through a full 22-degree arc, pushing the floating gate sector steadily across the Nieuwe Waterweg toward its counterpart. At mid-channel, the two gates do not slam shut. They stop short, leaving a gap. The tidal current does the closing. Water pressure against the curved surfaces drives each gate the final distance into the sill, wedging them together under their own hydraulic load. The harder the storm pushes, the tighter the seal becomes. Finally, the inner chamber between the gate and the dock is flooded to match pressure on both sides. This equalization removes the stress differential and locks the structure in place. The whole sequence, under 60 minutes. That is the design. What the design encountered on its first real test is a different matter. On the night of November 9, 2007, a depression moved across the North Sea. Forecasting models tracked it early. By 23, BOS had seen enough. Without human intervention, the computer issued the closure order. The ball valves opened. Water flooded the floating arms. Within minutes, two structures the length of the Eiffel Tower, lying flat, began rotating on their trunnions, sweeping 210-meter arcs across the Nieuwe Waterweg. The North Sea was still rising. By the early hours of November 10th, the surge at Hoek van Holland reached 2.8 meters above NAP. The gates met at the sill. Hydraulic load pressed them together. The seal held. For 14 hours, Rotterdam stood behind that wall. The port, the refineries, the low districts built on reclaimed polder, all of it protected by a hinge, a trunnion, and a decision made by software. Then the surge receded. BOS confirmed the threshold had passed. The inner chambers drained. The arms swung back. The Nieuwe Waterweg reopened to shipping. Rotterdam had not flooded. 54 years of hydraulic reasoning. From the dike failures of 1953 through the compromises of the Eastern Scheldt and the 5 failed design proposals and the decade-long debate over autonomous control had just been validated in a single overnight closure. 3 hours and 12 minutes. That number opened this account carrying almost no weight. Now it carries the full load of everything described above. It is the window between a North Sea forecast and an irreversible catastrophe for one of the most densely engineered landscapes on Earth. The Maeslantkering was built specifically to fit inside that window, and every element of its design, the arc geometry, the ball joints, the hollow buoyant sectors, the autonomous control system, the dry docks that look like riverbank, was a direct answer to something that failed, or nearly failed, before. No single element was innovation for its own sake. Each one traced back to a specific rejected proposal, a documented failure mode, or a political constraint the engineers could not design around, but learned to design through. The structure's current design assumes a storm that arrives once in 10,000 years, but current sea level projections place that level of surge inside the present century. Planning for the Maeslantkering successor has therefore already started. One gap in the delta works, however, remains unresolved. The next video closes that gap, and the engineering required to do it is unlike anything in the delta works that came before.